Today we are investigating a crime. Your cache told the user they had $100. Your database says they had 20. Someone is lying. And the scary part is your cache isn't even embarrassed about it. Caching is one of those engineering tools everybody loves because the promise sounds incredible. Add a cache, reduce latency, cut database load, scale effortlessly, and make dashboards look amazing in architecture reviews. Suddenly your 50 millisecond database query becomes 0.2 millisecond memory lookup. Everyone claps, you're happy, your infrastructure bill drops, your graph becomes beautiful. But there's a catch. The moment you introduce a cache, you create two versions of reality. One version lives in your database, which we call the source of truth. The other version lives in the cache. And from that moment onward, your system's biggest question becomes, which truth is the real truth? That's why this video is about. Not caching as a performance trick, but caching as a architecture problem. Because caching is not really about speed. It's about deciding how much lying your system can tolerate. And yes, that sounds dramatic, but by the end of this video, I want you to see cache the way experienced backend engineers do, not as a free optimization, as a trade-off. Alright, let's go. Cache looks innocent. Before we accuse cache of anything, let's be fair. Cache is brilliant. Without cache, your app talks to the database reads disk pages, traverses indexes, executes query plans, acquires locks, allocates buffers, serializes rows, this and that would take at least 50 milliseconds. Now introduce cache using something like Redis. The request comes in, instead of hitting the database, your application asks Redis, do you have users 42's balance? Redis replies instantly, yes, $100. Done. No join, no disk, no locks, no nothing, just RAM. That's why cache is fast. RAM access is dramatically faster than disk-backed storage, and because reads dominate most systems, cache can transform throughput. Suppose 95% of your reads become caches. Your database load collapses. One database server suddenly supports traffic that previously needed 10. That is why caching is everywhere. So yeah, everything, from browser cache to CDN to database cache, everything, even CPU cache. The cache is everywhere. Computer science is basically a giant story about avoiding slow reads. So far everything looks perfect, right? Which means it's time for things to go horribly wrong. Okay, the first lie. Let's say user balance is $100. If the database says 100 and cache says 100, everything is consistent. Then the user spends $80. Your payment service updates the database. Now the database says 20. But what about cache? Cache still says 100, and suddenly your system has split into two realities. Reality 1, the source of truth. Reality 2, fast, convenient, but fictional. Now imagine another request arrives immediately after the payment. User opens the app and checks the balance. Your backend hits the cache responds $100. That's wrong, right? Your system just served false information. That is the core problem with caching. Cache stores historical truth, but users want current truth, and those are not the same thing. This is why I say cache serves lies. Not because cache is broken, because cache is stale, by design. The moment data changes, every cached copy becomes a countdown timer towards inconsistency. The only question is how long until the lie becomes dangerous, right? So we know that not all lies matter equally. Here's where architecture becomes contextual. Not all stale reads are equally harmful or important. In banking, stale data is terrifying. Suppose a user sees $500, they initiated for $90. Transfer cash was stale, actual balance is 100. Now what? Maybe you reject late, maybe you overdraft, maybe money disappears into reconciliation hell. Financial systems usually demand extreme strong consistency. A stale balance can directly cause monetary loss. Now, consider stock trading. Prices move in milliseconds. Showing stale market data can mislead traders. And at high frequency scales, even 100 millisecond matters. Now, consider e-commerce inventory. This one is sneaky. Cash says 2 items remain. Reality says 0. 40 customers click buy. So yeah, congratulations, you oversold. Now support tickets begin. Now compare that with social media likes. Your post says 1200 likes. Reality says 1,000. But nobody cares, right? Your ego will survive. This leads to one of the most important architecture questions. What is your staleness budget? A staleness budget is the maximum amount of inconsistency your business can tolerate. Milliseconds, seconds, minutes, hours. If you don't know this number, your caching strategy is a guesswork, and architecture based on vibes is usually expensive. Cache invalidation. The real problem. This brings us to the part that gives experienced engineers trust issues. Cache invalidation. The core problem sounds deceptive because it looks simple. Whenever underlying data changes, every cache copy of the data becomes potentially stale. So the system needs a reliable way to either update or remove those cache values before user reads outdated information. That sounds straightforward until you realize the distributed systems are there. The most common strategy is TTL, as you can see. Or time to live. You cache a value and assign an expiration window, maybe 30 seconds or 5 minutes. Once that window expires, the next request fetches fresh data from database. TTL is attractive because it is extremely simple and cheap operationally, but the trade-off is obvious. Your system now explicitly accepts its stale window, meaning incorrect data may be served until expiration. The second strategy is write-through caching, where every successful database write immediately updates the cache as part of the same workflow. That is the key, the same workflow. This reduces stale reads significantly because cache stays close to the source of truth, but now writes become more expensive and reliability becomes trickier, since partial failures create awkward states where the database update succeeds but the cache update fails. The third strategy is write back caching, which optimizes for write performances by updating the cache first and persisting to the database asynchronously later. This can dramatically improve throughput under heavy write loads, but it introduces durability risk because a crash before persistence layer may result in lost writes. The fourth strategy is event-driven invalidation, where services publish change events through messaging systems like Kafka, or subscribers can invalidate or refresh affected cache entries. This scales well in large systems, but now consistency depends on event delivery guarantees, ordering, retries, and consumer reliability. And that is the important part. Every invalidation strategy solves one problem by introducing another. There is no perfect cache invalidation model, only trade-offs between complexity, consistency, and performance. So what is the final verdict? Caching is often introduced as a simple performance optimization, but framing is incomplete. That is why experienced backend engineers do not ask only whether cache improves latency. They ask deeper questions like, how stale can this data safely become? What happens when users observe stale data? And who absorbs the cost when cache returns outdated information? Because caching is never just about speed, and it is about deciding how much inconsistency your system can tolerate in exchange for performance. That is the real trade-off, and that is the trade-off engineering.